original source value. And furthermore, if you try and decode a function that was not a target value that was not included in the format, that is, there is no source value that is related to that target value under the format relation, you will get an error. So decoders are themselves partial functions. So in other words, if you get some garbage data in, you will say no, you will signal an error, and you will not continue processing. So here is the full definition of that relation. So here we have a format is said to be, a decoder is said to be a valid decoder for a format. If here this says that for every source value included in the format, you'll get, when you decode that, every target value included in the format, when you decode it, you'll get back the original source value. And this captures the fact that if you decode a target value and get some result back, that source value had to be included in the original relation. Okay, so obviously there's another way we could have defined decoder correctness, right? Arguably just as valid, where we leave off the second condition, right? And essentially what that says, in the case that you try and decode some junk target value, I can return whatever I want, and that's fine. Why did we choose not to do that? Well, it turns out that when you try and decode something that's junk data, once you decoded this data, you tend to pass it on to some client, and they're going to do something with it, right? Maybe they'll insert it into a database. I don't know what else they might do. They'll try and process it. And if you have junk data and you pass junk data along, that's a source of a lot of gross bugs, right? And so for the interest of security, we baked into our specification that you will recognize only things that are included in the format and nothing else. Obviously, someone might choose to relax this condition, and that's perfectly acceptable. I think the same methodology would apply. Specifications are part of the trusted code base, so I assume this is the right way to do it. Okay, so running a little bit low on time. So now there's a slight problem here in the sense that we've separated our formats. Our encoders and decoders, or these functions, are no longer related to each other, as you might expect, right? In the sense that the encoder doesn't talk, the specific function you get out doesn't talk about the decoder function in any way, right? But they are related by a common format, right? So we could squish together our notions of correctness as follows. And it turns out that if you have correctness of an encoder and decoder with respect to a common format, you can prove the expected sort of round-trip properties about these functions, namely that decode is going to correctly invert encode, as you would expect, and then encode will invert decode. This one's a little bit weird in the sense that it says if you decode a target value and you get a source value, and then you encode that source value, you will get some target value back. Why is that? It's because the encoder, the target has to recognize every possible encoding of a source data, and the decoder has to recognize every possible encoding of a source data, but the encoder picks just one, and so they might be out of sync. Of course, in the case that you have a format with a deterministic format with canonical encodings, this is exact. You are guaranteed to get back the same target value you originally decoded. Okay, so what's nice here? So what's great about encoders is we can play the same combinator trick that we did with decoders for encoders, and we can synthesize correct by construction encoders using these records that are just, again, a format, an encode, and a proof of correctness for the encoder function. So what's the right way to think of it? Well, the right way to think of it is that a format defines a family of valid encoding strategies, and a correct encoder just picks one. And if you look at this particular encoder for Word, well, it actually looks very similar to the format for Word. The only difference being that this one is not living in the non-determinism monad, but it still uses the same monadic bind operations. And so the equivalence is sort of tucked away into the notation, which is nice. And so synthesizing a correct decoder is actually a pretty straightforward game to what we did before with decoders. So we start off with some goal and we can apply a rule for how to encode words attached to something else. What do we need to do? Well, we encode the word and then we need to figure out how to encode the rest of the format. So this will give us a subgoal in cock. And now we just need to figure out how to encode the subformat. Well, we have an encoder for nats and we'll just work our way down. Eventually we get to the bottom where we've completely encoded everything. And now we can just work our way back up, filling up all these holes in this function we've defined along the way, do some simplification with the monad laws, and actually get out a nice function. Okay. Running a little slow, but I'll try and speed up really fast. So there's one interesting thing to note about, note about decoders when we're reasoning about decoders, the correctness of a particular decoder component. Typically, we intend for it to be used in a format as part of a larger format, right? So when a decoder is being used as a partial format, as part of a larger format, it's really a partial function in the sense that it's going to decode a piece of the target value. It'll leave the rest of the target value unchanged and then pass it further on for further decoding, right? And additionally, we expect because it's part of a larger format, it's probably going to be restricted in some way because it'll probably appear after something else. So we actually bake this into the true definition of correct decoders. We're actually going to bake this predicate in as a parameter of the combinator definition, and additionally, and so we're going to assume that it's formatted, and additionally we're going to represent the fact that these decoders are partial functions by saying it's going to return some source value and the unparsed part of the string, and this will get forwarded on. And we can use this to define combinators for these higher order sequencing formats. So as promised before, I can show you how we can build up a generic combinator for sequence that we could use to define that word sequence combinator we saw. So here, the way to read this is the correct decoder. Here's the format. Here's the decoder function you get out at the end. And here are all of the assumptions you need to satisfy in order to apply this rule. So what does it say? It says you need to find a decoder for the first part of the sequence, the first part of this format. It probably has some condition on it, some restriction on its source values. That restriction needs to be entailed or implied by the restriction on the overall source value. You'll note that in this combinator, we assume there's some projection of the overall format in the first part of the sequence. Why do we do that? Well, it would be sort of silly to encode the entire source value and then keep encoding stuff after it. Even though that's silly, it's not beyond the realm of possibility. And if you chose to do that, you could just make this the identity function, and it would be fine. Right, what is the, okay, so there's the second one. And then finally, and this is the key bit here, for the final assumption, this is I need to find a decoder for the rest of this format for the source type, but I get a couple things to work with here. Number one, I need to show it works for all possible values of this S prime, which is, is the domain, the codomain of this projection function. But I get to say this S prime satisfies some predicate. That's good because it has to by the definition of this decoder. And additionally, I get to restrict the format with the information that this projection of the source value is equal to this value I passed in. And this is precisely how we thread information along. And this works out. And this, if you instantiated this rule with the base type word decoder for word, this would all just sort of fall out, and you would have the rule for word sequence decoder combinator that I showed previously. Okay, we can play a similar game for the other higher order formats. Union, I'm going to skip over in the interest of time. The really interesting one here is what do we do when we get to the end of a format? So we've, in theory, decoded all the information we need to recover the original source value. Pretty cool. So how do we finish things up? So this rule has 4 assumptions. One, we have to decode the last bit of the format here, but after we've done that, we're all finished. We need to have a similar sort of restriction on the the source values, the projection of the source values that needs to be satisfied by this for this decoder function. And then we have two more rather interesting assumptions. The first of these says that for all source values satisfying this predicate, it is the case that there is some g, which is some arbitrary function. You can imagine the actual rule definition, it's a universally quantified, such that composing g with f and applying it to s will uniquely identify s. And then there's a little bit here about a decision procedure. So the third rule says the restriction uniquely determines the source value. That's good. That means we can recover it. And then we need some decision procedure for the source restriction. Why do we need that? Well, you can imagine someone could have put some wacky condition, some undecidable predicate here on their format. And if you don't have a decision procedure for it, this would amount to solving it could amount to solving an undecidable problem. So you wouldn't be able to properly invert the format. Okay, so just let's see what happens when we try to apply this rule to something. So here is the final state that we got to, the final proof state we got to when we were showing the derivation of that decoder before. What do we see here? So we have this rather long predicate restricting the source values. And we have a little bit of formatting the word. And when we apply this rule, we're able to synthesize this function. And why is that? Well, given all the stuff we have in hand, we can instantiate g with the constructor for our record type. And in addition, this decision procedure deciding whether or not this predicate is true is always true, it turns out, just by the definition of the format and the information we've accumulated along. So we can drop out the if, and we can build this, recover the original source value. Okay, so a reasonable question to ask is how do we actually build up this G? The tricky bit is figuring out what these decision procedures and this constructor have to be. And it turns out in one of these derivations, we can use tactics to automatically figure it out. We can actually use LTAC to synthesize a particular function G just using the constraints we have in hand, which is pretty cool. So I'm going to dive a little bit into some bits of calc that people may have seen before. So morally speaking, G here is an EVAR that represents a function. The goal state we get into after we apply this rule has an EVAR for this function that reconstructs the original source value, which is good. So if we look at the goal state here, we have some predicate on the source value, and we need to fill in this hole in such a way that whatever function we have here, if we if we apply it to S of payload, we'll get back the original S, the original function. Now, one thing you might ask is why not just use reflexivity at the start? Well, this is slightly problematic in the sense that when we applied the rule, S wasn't in scope, and so the S is not available for instantiating this EVAR. So we have to do a little bit more work to show how to recover this the original value using the data we have in hand. And it turns out this isn't too hard to do in general, well, for record types at least. So what can we do? We can destruct the source value S. We'll just use destruct, and that will replace all the occurrences of S with its constructor and some new fresh variables. So here S has become, a record with 3 new values, and we see those values up in our hypotheses. That's pretty great. And now all of these equalities that we've gathered up as part of parsing, well, we can rewrite with them. So we can replace all of these fresh variables or values, which I guess should be quantified here, but aren't, with these values we've decoded before. So now here we're going to replace x1 with this previously decoded value, and ditto for this previously decoded value. And all we have left to do is to show how to fill in this hole with a function that when applied to x3 will give us this value. And it turns out you can very easily define a tactic, higher order reflexivity tactic that'll do this automatically and solves the goal. And it'll just fill in this EVAR with the function that reconstructs the original source value. So the takeaway message is that with a little bit of LTAC black magic, you can actually synthesize inductive, or values of inductive data types automatically and rather generically, at least for records. Okay, I think that's enough sort of Narcissus details. What have we done with it? Well, Narcissus, as it exists right now, includes a library of common formats. So we have a sequence, we have some higher order combinators, sequence, termination, conditionals, booleans, blah, blah, blah. Interestingly, we have some sort of maybe more novel data types. So we have domain names, a format for domain names, which use this sort of wacky compression algorithm. And we also have a format for, higher order format for IP checksums, which is pretty cool. Again, these are maybe something you wouldn't include in a standard combinator library by default, but we could add them without too much trouble. Okay, having done this, we can actually synthesize encoders and decoders for the entire IP stack or the internet stack. And we did that, so we synthesized a decoder and encoder for Ethernet headers, for ARP, not headers, well, whatever they're called. I'll call them headers. Maybe data frames is what they're called. IP headers, UDP headers, TCP headers, and also DNS packets. And each of these sort of use non-standard or features of Narcissus that you wouldn't find in, say, a compiler for regular expressions. So interesting features. Ethernet, as I said before, has these multiple format versions, which are sort of wacky, but we can account for using our union combinator. IP, UDP, and TCP all have this IP checksum. IP has some underspecified fields, as does TCP. DNS has this weird compression strategy and also has variant types I alluded to before, so you can actually, when you have the response to a particular query, you're going to tag what type of response it is, and depending on the tag, you're going to choose to interpret the payload answer differently. Okay, so having synthesized these functions, we use a Cox extraction mechanism, which I believe we'll be covering in a little bit later next week or this week, to build get out OCaml implementations of these functions, and then we plug them into this Mirage OS operating system to show that, hey, this works, and hey, it works. We got some numbers out of it. They are reasonable. I guess it's hard to have a baseline here, but this is the time it takes to parse one packet in microseconds. So as you can see here, for a lot of the simple formats, Ethernet headers, ARP, IP headers, these are fairly fast. In the case of TCP and UDP, we have to calculate the IP checksum, which we're doing a little inefficiently right now. But it turns out, when you're actually running this on the production Mirage OS server, you don't even really notice the overhead because it's such a negligible part of the overall runtime. It's also interesting that Mirage OS doesn't actually check conformance with the format. So there are a couple of things in their test suite that aren't actually valid TCP packets, and they just pass them along. So there's the field that represents whether or not something's an option, and then you actually you encode the option, and they don't actually check that these the values you get are consistent in any way, which could in theory cause a bug, although it hasn't. Yeah, yes?
How does your performance compare to the native OCaml code that was written before you replaced it?
Yes, so the question was, how does this performance compare to the native OCaml code that we replaced it with? And I have to dig deep in my memory banks here. For these base formats, it's actually comparable. It's probably like a 5% overhead. For these larger packets, we're much more inefficient because of how we calculate these IP checksums. So the overhead is probably like 20x, I think, which, again, we haven't done too much optimization of the extracted code. So and in fact, with a little bit of optimization for the extracted code, we got like 100x speed up. So maybe we could be faster than the native OCaml version. Yes, that's all I'll say about that. Are there any other questions? Yes?
How does the number of lines of code compare to the OCaml?
Oh, well, that's it. So the question was, how do the number of lines of code compare to the OCaml implementations? Are you asking about like the specifications or like the synthesized functions?
Well, I'm interested in the comparison between the specifications in yours versus the implementations in there.
Okay. So it's actually I don't know those numbers off the top of my head. To do their part.